Hello everyone. In this short video, we are going to see Keras and an implementation of a model, which is a very basic model and which is also known as Hello World for deep learning. The handwriting, the number identification, handwritten number identification, that is going to be our problem. We'll be creating the model, we'll be seeing what exactly these terms mean, optimizer loss and activation functions. Post that, we'll be saving the model and the safe model will be reusing it. So we don't have to do the training job again. This is one time job, and then we are able to load the saved model and use it for predictions every next time we have to make predictions. So what is Keras? Keras is deep learning for humans. This is coming directly from the Keras website. So what it means is that it is a easy way to do deep learning. So let's take an analogy with the assembly language. If you have to write something on the assembly language, if you have to write a program in assembly language, it's so difficult because you have to do register manipulation, you have to do accumulator manipulation, you have to shift the bytes from here to there. So it's difficult to do programming in assembly language. So what did we do? We instead of using machine language or assembly language, we started using high level language like C++, Java, which abstracts all the difficulty and makes it very easy to code. The same thing with Keras also. It abstracts all the difficulties and makes deep learning and machine learning very easy to program. Keras has three different way to do modeling, deep learning modeling: sequential model, functional API, model subclassing. We are going to use sequential modeling here. So what is the problem statement? This is the hello world of machine learning, hello world of deep learning, whereby we use MNIST data for handwritten text, handwritten numbers basically, and we try to identify those handwritten numbers. Let me show you in a nice visualization, which is basically done by Adam H. Harley. Let me show you that. So this is the visualization from Adam. So I write any number here. For example, I write 2, and we are able to see that the machine has also guessed it as a 2. Second guess is 8, and we can see that this neuron, which is 2, it has been highlighted also. It has been highlighted as the number 2. So this is a neural network where we have one input layer and we have two hidden layers. These two are hidden layers, and we have one output layer, and we can see every neuron is connected to every other neuron from the input layer. Okay, if we see here, this is connected to every other neuron in the input layer. Okay, same thing becomes here. So this is connected to every other neuron. For this, the input is this. For this layer, the input is this, and for this one, the input is this. Okay, so we have the neuron which is being selected as highlighted one. If I take any other number like 3, the 3 is highlighted. Now we are going to see the same thing in program, how to do this in Keras. So here I'm using PyCharm. Let me start by showing you the requirements.txt. These are the libraries which I'm using in my program. I'll place the requirements.txt and the program in GitHub also, so you can refer it. And in the description, I'll put the link. Okay, so this is the one which we wanted to see. So let me start it in debug mode. I will simply right click and say debug program. I've already placed the debug point, a breakpoint here, so it'll pause here. Okay, so we have hit the breakpoint here. Now I'll go I'll just step inside. So F8 is basically for the step. And if you see, for example, if you want to see what exactly is MNIST data, this is given here in this link. And this link also tells you how to load the MNIST data directly from TensorFlow dataset, TFDS basically. And we are saying we want to load for the train data first, and with the information first. As supervised means that we should be having the label information also along with the data. Okay, so that's what it means. And we can, if we go to this console, we can quickly see the information. If I say print info, I am able to see the information about the data set as well, correct? So this is the data and all those details about data set. This is MNIST data base of handwritten digits. And the image data is containing the shape is 28 by 28. This is basically the pixels 28 by 28, and one is the image. It's a grayscale, so it is one layer. There are no three layers for like in RGB we used to see, so it is only one layer. Okay, so that's what this information about this MNIST data set. We download the test data set also. Let me do a F8, and this is also done. So now what we are going to do is we are going to wrangle the data. Okay, we'll see what the meaning of wrangle is. Let me go inside the function by pressing F7. So if I go here, what we are trying to do here is we have this data set wrangling. We are mapping the data set, and what we are saying is that the pixel value, the intensity value, which ranges from 1 to 255. What we want to do is we want to make it range from 0 to 1. Okay, it is advisable. It leads to good results of prediction. So that's what we are doing. We are making the pixel range from 0 to 1. So how we can make them range from 0 to 1 is by dividing them by 255. Okay, so that's what we do on the image part of it. The label part, we don't do anything. We retain the label as is. Okay, so label, there is no change. Only the image pixel values we are changing. Then I go here and see all these details, like for example, what is the meaning of cache, or what is the meaning of this data set map which we have done. All those details, there are hyperlinks here. You can go and see in detail what exactly this means. The caching of data for fast processing is done here. And then because we are doing a training, we want to shuffle the data. And this shuffling is to ensure that we generalize. Okay, we make a general model and not memorize. It should not be trained on the trained data. It should not be giving so good results, but on the validation data it is giving bad results. That means the model is doing memorization. So we don't want to do a memorization, we want to do a generalization, and thereby we shuffle these images which are coming. So it's like all the zeros are given together, or they are shuffled. All the images are shuffled. So we prefer shuffling. The last part is basically how much batch size should be there, and prefetch, like how much prefetch should be done. We can ask TF to take TensorFlow to take a decision on prefetch on its own. Okay, so let me quickly show you how you can see this all details in the web also. So I am here in this page. So you can see a TensorFlow dataset. You want to see what is the meaning of cache. You can go here and see what is the meaning of cache. Caches the elements in the dataset. You want to see how to use map. This is how you use map. They have given all the information, and I've put the hyperlink on top of the code also. You want to see take. Okay, take is basically from the dataset you want to take any number of items, like this we'll see in a bit, but that is also here. You have the reference document for that as well. For everything you have a reference document. Okay, so I do a F8 and I go outside this, and the same thing we are able to do with the test data also. Now we are going to create the model. So how to create the model? Let me go inside the function. So what we are doing, like I told, there are three ways to create a model. We are going to use sequential model because it is the easiest one. The first thing which we have is the input layer. So the images are 28 by 28 pixel with grayscale. So that is going to be our input layer, and then we flatten. Flatten means we are basically converting it into a vector which would be of the size 28 into 28. That is what flatten means. We'll see when we print the model summary, we'll get these details. Post that, we have introduced two dense layers, 300, 100, and finally the output layer. Okay, and we see that we are using some activation functions also here. So what are these activation functions? Let me quickly go to the meaning of dense layer activation function. Quickly, I'll just quickly go there. So dense layer, we briefly touched this topic earlier also. So in dense layer, what happens is every neuron is connected to every other neuron. Okay, in the upcoming layer. So that's what is the dense layer. So dense layer receives input from all the neurons of the previous layer, and thereby it is called dense. Activation function. So activation function, basically it introduces non-linearity into the output of the neuron. The explanation of what non-linearity is beyond this tutorial, we'll see it some other time, but this is basically whatever output you receive. uh, uh, so let's see in a bit. So these are the two activation functions which we have used: the ReLU, which is also called rectified linear unit, and it takes the maximum of 0 and the value itself. So basically what it is doing is it is getting rid of all the negative numbers which are there. And softmax generally is used in the last layer, okay, last output layer, and it is for probabilities. So for example, here we have to predict which number is it. So what is the highest probability of that number, which can be indicated with the neuron which has been lit. Okay, so that is what softmax gives. And here is a simple code. How can you do a softmax? Basically exponential and division of the entire with the sum of all the exponentials which are possible. Okay, so this is what softmax is. um, See, and then we have these two concepts of loss and optimizer. This is also going to come in a bit. So loss is what we want to minimize. Okay, we want to be as near the result what we are going to predict as possible. So for example, in the training, if we are sending a 0, the output neuron which should be lit should be 0. Okay, same for any other number like 4. If the number being sent is 4, we want the neuron with the 4 to be lit and indicate that it is 4. Okay, optimizer is the way how to minimize the loss. Okay, and these are the different optimizers which are possible. And as you know, regression and classification, two major streams of machine learning. So this is a classification because we are going to classify whether it belongs to, whether it is a 0, 1, 2, 3, which number is it. So basically it is a classification, and we are going to use this loss function here. And regression is like, for example, prediction of a house price. Okay, those kind of problems are regression, and there the loss functions are little different. And optimizer which we are going to use is Adam optimizer. We are going to see it in a bit. So okay, I'm back from the detour. So we have seen what is a ReLU activation in a bit, and we also saw that the last output layer should be a softmax because it gives the probability of which neuron is lit, thereby giving the result of which number the input is. Okay, so I do a quick F8. So now I have to call a compile model. Let's see what is inside that function. So I go here by pressing F7. So again, the same thing which we discussed, the optimizer and the loss. Loss is what we have to minimize, and how we have to minimize is by using an optimizer. And we have to have a matrix, and we are using accuracy as a matrix here. So let me do this quickly. So this is basically the model summary which is printed here. So if we see our model, what did we say here? 28 by 28, which is 784. Suppose we flatten this, it becomes a vector of what is the length? It is 28 into 28, which is 784. Okay, and then the second layer had 300 neurons, the third one has 100, and the last one was having 10, which we are seeing here. So that is being indicated in the model summary. Let me press F8 and go further. So we have done the model compilation and we have created the model basically. Now what we are going to do is we are going to fit the model, and let me quickly do a F8 and we would be able to see the same, the model fitting here. So we have chosen 5 epochs here. Basically, it has to be the algorithm shall be seeing the data 5 times, and every time it will try to learn from the previous run and try to optimize, meaning that it will try to reduce the loss. Okay, so we are seeing that the accuracy is 98.90 here. Now the model is all created, and we can do a evaluation on the test data. So if I do a evaluation on the test data, so it says that in the test data it has little bit reduced accuracy, around 1%. So 97.93 is the accuracy on the test data. Okay, now if I have to plot the model, so this is basically plotting the model, and for this only the graph viz and PyDot is being used. So if you are a Windows user, you have to install GraphViz separately. Also, there is a exe which you have to install. Only pip install will not work. At least it did not work on my machine. Okay, so I go back to the code and I do a F8. When I do a F8, this is going to be this one is going to be created, and if I open this image, this is what it is showing me. So this is visualization. This was the input layer. We flattened it and it became 784. Then we had two dense layers, and finally the output layer, which was having 10 neurons. So this saved model which we have saved here, now let's see that this is saved. I could have done it in a separate program also, but let's continue it here, and we will try to run it against some images and see what is the accuracy which we get. So the model has been loaded. I do a F8, and it shall print the same summary which we saw earlier also. The loaded model, because it was saved this way, so the save summary is the summary which we are seeing here also. Now, what I'm doing is from the MNIST data set, the test data, I'm taking first five images from there. Okay, so if I take the first image, which is basically the example 0, and example 0 is going to give me the content of the image, the pixels of the image, and 1 is going to give me the label of the image. Okay, example 1. So let me see what was the image. So if I see what was the image, it printed that the image label is 2. Okay, so let's see what our our model predicts this image as. So I press F7 to go inside this function. I am using pyplot to plot this image also, so that we can see it is really 2 and how it looks. So I go and do a F8, and this is 2. So the image which we are sending to the model is 2. It looks like this. Let me quickly close it, and I go inside this again, F8. I convert this image to an array, and I expand the dimensions, and then finally I predict it. Okay, when I predict, this is basically going to tell me that which neuron is being lit. So basically the first 0, 1, 2, so second one has been lit. So with argmax, what argmax does is it will tell you which argument is lit. So for example, it is a second argument, which means the model has predicted it to be a number 2. So if I do F8, it is going to tell me the same thing, that the image label is the predicted value is what, 2. So we had 2. The model has predicted the same. Let me run it one more time. So if I go here again, I do F8. I see that this is basically the number 0. And if I go inside, I do F8. It shows a number 0. I close it, and again I do, let me put a breakpoint here to move little quickly. I do F8, F8, and I do execution here, and we know that this was 0. It was predicted also 0. Again I went to a number 4. Okay, we see number 4. I quickly run it, and I see a prediction of the same. Okay, so The last one was 7, it was predicted as 7. It was 4, it was predicted as 4. So that's what it is all about. I'll try to place this code in the GitHub also. Let me quickly give you a peek view here. So this is what the imports which we discussed. This we are setting so that unnecessary warnings are not getting printed. You can read this message here. So info and warning messages are not printed if we are setting this log level. Okay, we saw that we have to create a model. After creating the model using the sequential APIs from Keras, we are compiling the model where we are mentioning the optimizer and the loss. Okay, and we are using the same model and we are fitting the model in the test data. Okay, test data has sorry, not the test data, the train data. The train data has both the labels and it has also got your image data. We are running it for 5 epochs and then we are saving the model. After saving the model, if we want, we can plot to see how exactly the model layout is, and post that we are testing the saved model. So if we have to test the saved model, we can do it in a separate program. Here we are doing on the same program. We load it, we load the model, and then we take some 5 images. These can be taken from the disk also, but I'm taking from the same model some five handwritten images, and then predicting the value of the images, the numbers which are there in the images. Okay, thanks. Thank you very much.